The parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
All right, everybody, welcome to our Saturday afternoon edition of the Strathmore Speaker Series. I'm Scott Lipkowitz. For those of you who don't know me, I am the Digital Services and Technology Librarian at Onondaga Free Library. And I would like to thank you all for joining us this afternoon and for watching Perseverance land once again, as a little intro there. But before we begin with our event, I just want to say thank you first to Jeff Megivern for taking the time out from sunny California today to talk with us about what it's like to work on one of these missions, and also to the Strathmore speakers for allowing us, Onondaga Free, to bring this insightful and thought-provoking programming to you, our patrons, and our community members. And with that, I'm going to first turn it over to Mary Beth from the Strathmore Speakers, who's going to introduce our guest today. And then we're going to do a little bit different. We're going to do more of an interview style. If you've seen one of the previous events, we usually have a lecture. There's going to be a little more informal interview style. And then at the end, once we are finished with the interview, we'll open it up for questions from the audience. So if you do have any questions, feel free to type them in the chat and we'll ask Jeff at the end. So I'm going to give it over to Mary Beth to do our intro.
Hi, everybody. I'm Mary Beth Horsington on behalf of the Strathmore Speaker Series. Thanks so much for stopping in here today for our fifth event of the 2021 season. We used to hold these events at the Fire Barn in Onondaga Park in the Strathmore neighborhood, but COVID necessitated a switch to Zoom. The Onondaga Free Library is providing the technical assistance we need to bring you this program, and we thank them for their expertise and generosity. The Strathmore Speaker Series is made possible through the support of the City of Syracuse, the Gifford Foundation, and the Greater Strathmore Neighborhood Association. Our guest speaker today is Jeff Megivern, a NASA engineer who was on the team of the Perseverance Rover's successful landing on Mars February 18th. He'll tell us about the mission and the challenges of robotic exploration of the Red Planet. Then he'll give us an insider's look of the NASA Jet Propulsion Laboratory. Jeff grew up in Florida, right across the river from Kennedy Space Center, where he watched launches from his backyard. He earned bachelor's degrees in engineering and math at Florida Institute of Technology and interned at Kennedy Space Center. As part of this internship, he sat on a launch console for a number of launches. Jeff later moved to California to work at Pratt & Whitney Rocketdyne as a system test engineer. He currently works for NASA JPL as the Systems Engineering, Integration, and Test Lead for the March 2020 Sampling and Caching Subsystem. After Mr. Megivern's talk, there will be a brief question and answer session, so be sure to stick around to the end. And now, please welcome our speaker, Jeff Megivern.
All right, so I'm going to get myself up here so we can have a little dialogue here. So Mary Beth just introduced Jeff a little bit, but Jeff, can you tell us a little bit more about yourself? You know, where did you come from? How'd you get to where you are now? How'd you get to be making robots that go to Mars?
Sure. So like Mary Beth mentioned, I grew up in Florida, right across the river from Kennedy Space Center. So when she says I watched launches from my backyard, I quite literally watched launches from my backyard. We'd frequently get up on the roof and watch them launch up through the trees. So I got into a lot of amateur rocketry as a kid. In high school, there's competition called Team America Rocketry Challenge. And so in high school, me and a few of our friends got together and we built a rocket and competed in this national challenge, went to Washington, DC and did all that. So coming out of high school, I had the bug. Growing up with it, participating in competitions like this with friends, I was on a path to the space program. So when I started undergrad at Florida Tech, I got involved with the co-op program there. The co-op program is an internship program where you participate in an internship every year. And so I was interning out at NASA Kennedy Space Center, and that's where I worked the launches. I was interning with an organization called the Launch Services Program that concentrates on all of what we call the expendable launch vehicles, so the launch vehicles that we weren't reusing. So at the time, it was a lot of Delta II launches, and I sat console on missions like the Mars Exploration Rovers A and B, so those are Spirit and Opportunity rovers. I worked those launches. Of course, I was a student, so I wasn't providing all the engineering expertise associated with the launch, but it's great to be in the middle of all that. So after I graduated, I moved out to California to work at Rocketdyne. Rocketdyne's a rocket engine development company. They've engineered a bunch of other things over the years. They've been around for a long time. And so at Rocketdyne, I was working on an engine called J2X. It was the upper stage engine for the Constellation program. The Constellation program can be thought of as the precursor to what's the Space Launch System now, SLS. So the J2X engine's upper stage, liquid oxygen, liquid hydrogen, 300,000 pounds of thrust. We could talk about all of the nitty-gritty details of a rocket engine if you want. And so I was at Rocketdyne for about 10 years. I actually spent a couple years in the middle at Jpl in New Hampshire. And I did that to get closer to my parents, who at the time were actually living in Interlaken over between Cayuga and Seneca Lakes. So let's see. After I was at Rocketdyne for a while doing different rocket engine development programs, I moved to JPL about 4 years ago, and I started at JPL to work on Mars 2020. So I hired in to work on the sampling and caching subsystem. So you'll hear me, I'll say SCS for short. So the sampling and caching subsystem, we can get into this a bit, is part of the system that is drilling into the soil, collecting samples, storing samples, and doing everything to prep for the first phase of a Mars sample return mission. So I was leading, oh, yeah, you have a question, Scott? Oh, no. After leading a big system development campaign for SCS, doing environmental testing, just a couple months ago, I actually started a supervisor position in a group called the Materials Development Testing and Failure Investigations Group, and that's my position now.
Cool. So let's so first off, what is JPL? So you mentioned JPL there a little bit. So what is JPL? And then can you tell us when you were hired and they brought you into the room and they said, okay, Jeff, we want you to build this system that's going to drill into rock on Mars and send it back to us. How do you, I'm sure most people think that's probably very daunting and wouldn't even know. So what's it like in the room when you're planning for the mission? And then how do you start thinking about how to solve this really interesting problem?
Sure. So JPL is the Jet Propulsion Laboratory. And JPL has roots in the space industry back to the 1930s. We were started by a few students from Caltech and their professor, Dr. Von Karman. In, I think it was 1938, they started to get into propulsion development work. So started to get into rocket engine work. And over the years, as JPL as a small organization grew and grew and grew, they eventually, and we are today, a federally funded research and development center. So we're known as an FFRDC. So a federally funded research and development center. What it really means is a federal organization, and in our case, NASA. NASA owns the facility. So NASA owns the labs, NASA owns the buildings. When we want to make big changes to the infrastructure, we contact NASA. But most of the employees, most of the folks that are working at JPL, and most of the folks that are making sure the labs are running and the missions are built and everything's developed, work for Caltech. So I actually work for Caltech as a JPL employee, and that's common at JPL, very common. There's a handful of NASA specific employees, but most of us are Caltech. So there's JPL. And okay, so you asked coming on board to get into Mars 2020. So the curtains aren't opened up, right? So when I started JPL, it's not this is what the wizard looks like, right? I have to travel the Golden Brick Road to really understand, because it's a complex system. And so when I started, for me personally, it wasn't Jeff developed this rover. Go do it. No, it was more like, Jeff, here's some systems, learn about these systems. And some of the very first things I did was led some actuator development testing. So the sample caching system, SCS, is a pretty complex system. We have 17 actuated mechanisms and joints. And what that means when I say actuated, it just means there's a little motor at each of those joints and each of those mechanisms that are doing something. So it's probably easiest to talk about the robotic arm. The robotic arm has 5 joints, so 5 motors, 5 points where the arm can move and get to the surface. And so 17 of those motors. And so at the time, we were trying to understand what performance those motors had and how to control those motors. And I was leading the effort to test those motors for the sample caching system. And so getting into that, I start to understand some of the details, and then getting into this bigger sample caching system test campaign. I had some system test experience from Rocketdyne, so I was comfortable with the system test aspect. But now you enter in this big complex system in a big chamber. We were in a 10-foot chamber, 10-foot diameter chamber, flooding it with liquid nitrogen, taking it down to -70 degrees Celsius, pumping it down to 7 torr. So taking it essentially Mars conditions, Mars temperatures and pressures. But to take a step back, like what is it to design a mission like this? What is it to make a rover like this? So Mars missions at some level have been thought about for a long time. And if we think about the current idea of what we think a Mars mission is, in the 1960s, right when we were hot and heavy in getting Apollo going, we were trying to get to the moon. There was this other effort to really explore our entire solar system and try to get an understanding of the deeper space. So in the mid 60s, there was a program called Mariner, and we were sending spacecraft to Mars with the Mariner program. And so there are some aspects you could say it takes 50 to 60 years to develop an idea to get to a point where now we are actually talking about getting samples and bringing them back to Earth. And up to this point, we were talking about it conceptually, but we are designing hardware to do that. We are designing a mission to do that, to go and get samples and bring them back to Earth. Right? So in the 60s, it was just taking pictures. The Mariner program was giant, took all of the early pictures of Mars. We landed on Mars for the first time. And so all of that is the historical backdrop and the technological developments that are needed to be able to do what we're doing today. And today, it takes 10 years, you could say, for a big giant mission like Mars 2020 to go from concept to launch. In our case, we were officially funded in 2014, so it took 7 years, but we were riding on the back of Mars Science Lab and Curiosity and all that. So there, I kind of skipped around your question a bit, but
that's quite all right. So what's the ultimate goal? So your part of the mission was first working on the arm and then now returning Mars rocks to us. But what's Perseverance looking for, and how does that build maybe on the other previous rovers like Spirit and Opportunity that people might know about?
Yeah, so all of our rover projects are looking for a couple things. We're looking for life. We're looking for water. We're looking for water mostly because our understanding of life needs water. And we're trying to just understand Mars. So we're trying to understand what the rocks are made of. We're trying to understand how similar it is to Earth. We're trying to understand the history of Mars so that we can understand the history of Earth. Like there's a lot of context of just trying to understand ourselves by trying to understand that. Perseverance specifically, we have 4 primary science objectives. So we're looking for life. We're studying the climate, we're evaluating geology, and this is the first time that we're taking specific actions to get ready for human exploration. And then that comes in the flavor of an instrument we have called MOXIE. So that's the Mars Oxygen In Situ Utilization Experiment, something like that. The idea is it's taking in Martian atmosphere and going through this big electrolysis process and outputting oxygen. So taking in the atmosphere and taking out oxygen.
One question too that I was going to ask you. So once it launches, so that's the mission. So you've done some prep work. Once it launches, what are you doing while it's en route? You know, how does that, is everybody just kind of hoping that it gets there safely and keeping their fingers crossed? You know, what do all the systems engineers do while Mars is on transit, and how long does it take to get to Mars?
So at the shortest, which is what we set up for, it takes about 7 months to get to Mars, roundabout. And that you can imagine the Earth orbit and Martian orbit are slightly different because they're slightly different distances from Earth, and they're elliptical in slightly different ways. So every 2 years, they get into that position where it's a 7-month trip. So every 26 months, Mars and Earth line up so that we can launch and get there in 7 months. And you can imagine launch is a giant milestone. And so up to launch, we're doing as much as we can to verify and understand the hardware, verify and understand anything we can physically change on the rover. Because after launch, we can't physically change anything on the rover anymore. After launch, the only thing we can change is software. So up till launch, it's all about testing hardware, seeing what breaks, understanding if it broke, and then fixing it if it broke, or addressing it if it broke, and tackling it that way. After launch, there's different teams caring about different things you can imagine. So there's the team, they're the cruise team. So we call our trip to Mars cruise. We're cruising there. So that team is recalculating trajectories, looking for where we're going, making sure we're still headed in the right direction, and then doing different trajectory maneuvers on the way. And all that means is every now and then on the way, they fire the rocket engine and make sure we're going the right direction, make sure we're oriented in the right way. And so that team cares about that. They care about that on the cruise. They care about that's what they care about for actual cruise. We're doing some tests on the way to make sure different systems are working on the way. Usually, mostly communication systems to make sure that we can communicate on the way there. That doesn't mean that we're not doing other things on the ground on Earth. So my test program, the majority of my test program was during the cruise phase, or at least a big chunk of it was during the cruise phase, because we wanted to make sure that we had a software load that we could use once we get on Mars. And so in a few months, when we go to start collecting samples and drilling into the Martian surface, we will have made sure that all of the software and sequences we have loaded are appropriate for what we're trying to do. And so the team on the ground then is testing hardware still, but not to see if it will break or to see if they need to change something in the hardware, to make sure that the sequences and operations and order that we do a thing work.
Cool. So
maybe Scott, should I talk a little bit about, because I realized I skipped over this, should I talk a little bit about what the sample caching system does?
Yeah, and actually I was thinking too, before we get to that, there are actually two questions that came up in the chat that actually are appropriate for right now for what you're talking about doing the testing phase. So one is from Sophia Jacobs, and she asks about the materials. Like, where do you guys get the materials from to build the rover? And just generally, do you like making things? How do you, are you a maker by nature? And then we also had one that kind of ties into this too, which is from Garrett Turberg. And I guess he took the JPL tour with you. And he said, yeah, there's a Faux Mars landscape area. So maybe you can talk a little bit about that too, since we were on the topic of testing and building and things like that.
I would happily talk about that. So materials, great question. Now I'm in a materials organization. We are limited to materials on Earth. We haven't started mining asteroids for whatever they're made of. So, common materials, aluminum and titanium and things like that, different seals. We have different seals that are made of a variety of different things. Teflon is common. And so what was the other half of that question? Oh, do I like making things? I can talk more about the materials. Should I explore some aspect of materials?
What's the rover mainly made out of?
Aluminum.
Mostly aluminum. Okay.
Mostly aluminum. It's light and relatively strong. That's kind of, we have a lot of weight restrictions on our spacecraft, and so we have to focus on things that are light. So all of the big structures are aluminum, different varieties of aluminum. We have a whole variety of materials testing that we do for all of our missions, not just the Mars mission. So we look at where a mission's going to be, whether it's on Mars or maybe it's on Europa, the icy moon of Jupiter. Maybe we're headed towards the sun. Maybe we're staying in Earth orbit. All of those different potential missions have different environments that they're going to be in. We have a space environments group, so different space environments. And based on those environments, we want to make sure that the materials we use and the process we use are going to stand up to those environments. And so we'll do a lot of environmental simulation testing where, let's say you have two things joined together. Let's say I have two coupons joined together. We'll thermal cycle them. So we'll take them hot and take them cold and take them hot and take them cold. We might do some, if there's going to be a radiation environment, sometimes we'll do some radiation testing. And then we might pull them. We'll do a tensile test, we call it. We'll pull them apart and see what kind of load they take. So we'll have, it's all about managing our risks, understanding what our risks are, and then testing away or designing away those risks.
Going back to Garrett's question for a moment, so how Mars-like is the faux Mars landscape? Is it also contained in a tube, in a sphere that replicates the environment, or is it just kind of for terrain purposes?
Yeah, so we don't have a biodome situation.
Okay.
It's the Mars yard. That's what we call it on lab. So the Mars yard is primarily terrain. So we have a group of geologists on lab and a whole team called the Extra.
Oh, shit.
Oop, 1 second, Jeff.
You muted me, bud.
There you go. So apologies, I was trying to get some. Okay,
so we have a team called the Extraterrestrial Simulants team. It's a couple of geologists, a couple of engineers, a couple of material scientists. And the Extraterrestrial Simulants team is responsible for understanding what other planets are made of, and then finding things on Earth that are like those things. And so we have a lot of partnerships with various farms and ranches in California to take a pickup truck and drive up on their land and go pick up some rocks and bring them back to the Mars yard. And so the Mars yard it's all terrain. It's all obstacles and rocks and different terrain features to simulate what we're going to encounter on Mars. And we have a big ground test, Earth-based rover that's equivalent to Perseverance. Our ground rover is called Optimism. So we use Optimism to do testing on Earth to understand how we're going to use the same thing on Mars.
That's really cool. So for all the kids who are listening, there's a cool job you can do where you get to build fake alien worlds here on Earth. So that's a fantastic career for everybody.
Well, and Scott, you're not wrong in what you're saying. In some cases, we don't have things on Earth that are like the things in space, and we have to make them. We'll do things like mixing styrofoam with cement to make like an aerated comet-like sort of thing. And so we make ice in different ways, because ice that naturally forms on Earth is not like the ice that naturally forms on Europa. So we put ice in a vacuum and we let the ice form in a vacuum rather than just getting it cold. So legitimately, kids, you can make space stuff here on Earth.
Yeah, that's cool. So now that so Perseverance is actually, well, I guess it's on Martian stuff. So what is the sample, the part of that mission? So now, Perseverance is roving around. What is the mission the part of the mission you're currently working on, the sample return?
Yeah, so the sample caching system is addressing a couple aspects of science of the mission. So we're addressing that geology aspect. We're addressing that looking for life aspect. And we call the looking for life, we call astrobiology. So astrobiology, geology, and sample collection. So like I mentioned, Mars 2020 and the Perseverance mission is the first phase of the sample return mission, the Mars sample return mission. So there's a whole big system on the front half of the rover called the sample caching system. And the sample caching system is a big robotic arm. So we use our left arm for the big robotic arm. It's about 7 feet long, and it has a drill on the end. So at the end of this drill, there's 2 stabilizers. If we find a rock that we want to drill into, we place the drill onto the rock, and then we extend the drill into the rock. So we place the stabilizers, and we extend the drill into the rock. And our drill is hollow. Our drill has an empty core in the middle, and we put a tube inside that core. And so then when we drill into a rock, we're filling up the tube with the rock material. Then we snap the rock off, and we bring the robotic arm back to the rover body. So we bring the sample. We take a picture of it. We use the mast, the head, to take a picture of the sample, and then we bring it back, and we'll drop the tube off. We'll actually drop the entire drill bit off, and then that drops it off to the bit exchange system. And we have this big bit carousel. So because we have a number of bits. And we rotate this bit carousel, and the bit goes from being up here to being down here. And underneath the rover, we have another robotic arm. This is called the sample handling arm. We use our right arm for the sample handling arm. So you have the big robotic arm up front. You have the little sample handling arm underneath. So I dropped off this drill bit with a tube in it. We move the sample handling arm over to the drill bit with a tube in it. We stick the sampling handling arm into the drill bit, and we pull the tube out. So now I have a sampling handling arm with a tube on the end. The tube's about the size of a whiteboard marker, the sample tube. And we do some things with that. Well, we want to understand how much sample we have. So we have a rod, and we measure how much sample's inside the tube. We take some pictures of the inside of the tube before and after we seal it. So we hermetically seal all of these tubes. So we take some pictures of it, we drop a seal in it, and then we squeeze this, we essentially deform this metal seal into the tube to get it to seal up the tube. And then we put the tube away. So now we're doing that. We have 42 tubes. The plan right now is to bring 30 of them back to Earth. So we do that, let's say we do that 42 times. And the rover had, let me pause there actually. There's the sample caching system. I'm about to launch into Mars sample return stuff. But I wanted to pause and see if there's any questions or whatever about.
So why, before we get into the actually sending it back to Earth and all the fun that entails, why was the specific site where Perseverance landed, why was that site chosen? What's special about it, and why there?
Yeah, awesome question. So we landed in the Jezero crater. What's so interesting, and if you have a picture of it, Scott, it would be awesome to show. But what's so interesting about the Jezero crater is it has the terrain features of what we see here on Earth at the end of a river, where a river delta, where a river dumps into a larger body of water. And the Jezero crater, one side of the Jezero crater has these same river delta features. So those delta areas here on Earth, if you think about the Mississippi Delta down where the Mississippi River, so there you go. If I didn't tell you this was on Mars, you might say this is a picture from Earth. You can see on the left there a thing that looks like it might have been a river, and you see these features, these streams that dump into the crater. So it's the crater, the right 2/3 of that picture is Jezero crater, and then the left side is outside of the crater. So imagine a river flowing down this river and dumping into Jezero crater, and it's not too far to say Jezero lake bed, right? Deltas have some of the highest density of unique life. And they're so life rich here on Earth. So if I'm sending a mission to Mars to find life, I'm going to send it to where a river is dumping into a lake.
Yeah, that definitely looks like it could be something that's here on Earth. So once we get the samples My biggest question, I guess, is how do you get them off the surface of Mars and back here? Are there tiny rockets inside the robot? Is there an orbiting satellite, or is there some cool physics trick that we use to get this off the lake bed and back towards Earth?
Yeah, no, we haven't invented new physics. We're gonna stick to the old method of launching rockets off of places. So I'll tell you a little bit about the Mars sample return mission. So if Mars 2020 is the first phase, the sample collection phase, so we're going to get the sample, and where I left off was the bottom of the rover now has all of these tubes in it filled with different rock samples that we picked up while we're traveling across the surface of Mars. I'm going to drop those off in a place, and the way the mission's set up is I'm going to pick up about a dozen samples, and I'm going to pick up 2 samples at every location, and I'm going to drop half of those off in the final drop-off point, and I'm going to go and drive somewhere else to get the rest of the samples. That's kind of the way the mission's set up now, and it's subject to change since we haven't started doing sample collection yet. So now you have the caching part of the sampling and caching subsystem. The caching part isn't caching the tubes on the bottom of the rover. The caching part is dropping them off on the surface of Mars. So the plan then is to drop a bunch of these tubes onto Mars. And in the meantime, we're developing the Mars sample return system. What's unique about the Mars sample return piece, and the JPL piece of it is called the sample return lander, is it's a big collaboration between a bunch of different NASA centers, so like Goddard and Marshall Space Flight Center, JPL, and the European Space Agency. We call them ESA. So you have NASA, JPL, and ESA, and then a bunch of industry and university partners coming together to make this monster system. We're going to use 2 or 3 launches to get there. We're going to have something orbiting around Mars. We're going to drop a lander off on the surface. We're going to have another smaller rover pick up some of the tubes and stick them into the lander. And we're going to have a rocket on that lander to take off from Mars, meet back up with the orbiting thing, and then bring that back to Earth, and then crash land into Utah.
Why Utah? Just because it's the
so
is it the rarest state? Is that why it's like a nice target?
They didn't keep up on their taxes.
Yeah.
So Utah, because there's a lot of space in certain parts of Utah. So you have a pretty wide band of potential error, and you'll still hit your target. But also the rocks in those areas are sufficiently different from Martian rocks that if a tube splits open, we can tell the difference between what's a Martian rock and what's a Utah rock.
Oh, cool. Yeah, that's very interesting. So if anyone in here today with us knows anyone in Utah, tell them to duck.
Give them a heads up. Yeah. We're a ways out. We're probably about 10 years from, at best, having samples back to Earth.
So Perseverance also has a little buddy, a little helicopter that I think hopefully everybody's seen the videos. They're really cool of Ingenuity flying along there. Can you tell us a little bit about that? And also what's that component? What is Ingenuity trying to is contributing to the overall mission?
Yeah. So I think it was 1997, JPL sent a mission to Mars called Sojourner, or Pathfinder. The Pathfinder mission included a little rover about the size of a remote control car. It had a little camera on it, it had some instrumentation on it, it had a little antenna to talk back to the lander. The entire purpose of Sojourner was to say, yeah, we can drive a remote control car on Mars from Earth. And that's what Ingenuity is to things that we can fly. So Ingenuity, in essence, is it's relatively simple. Folks on the Ingenuity team are going to slap me for saying it's simple, but it's relatively simple. There's still a lot to develop because now you're dealing with a lower density atmosphere on Mars. So there's less Martian atmosphere to lift up with. And so now you have to have bigger propeller blades, more surface area that are spinning faster than you would here on Earth. So now we have a drone that has to operate in a CO2 environment, spinning faster with larger propellers than we're doing on Earth, and we have to control it remotely 290 million miles away. So, and it's all sequences, right? There's not someone on Earth with a joystick flying the helicopter. We have packaged sequences, and we send those sequences to the rover, and then the rover says, "Okay, Ingenuity, go fly." So we call that a tech demo. It's a technology demo, and so we're trying to demonstrate that we can fly on Mars, and we've demonstrated. I mean, we're flying. And the only instrumentation on it is a camera or a couple cameras and a solar panel.
Cool. So yeah, I mean that's also a fun future career. You just get to play with toys and on Mars and design totally new systems for totally new environments. One thing that I thought was interesting that we could talk about is the fact that recently Ingenuity had a little problem with and it wasn't able to fly, and I think that was software related. But I thought that'd be interesting, because we see the triumph. Here's the video of Ingenuity and it's flying and it's amazing. But I think people don't realize how much troubleshooting and problem solving goes into engineering. And so what do you do, one, when the rover is 293 million miles away and it won't fly? How do you problem solve that, and how do you overcome it?
So I'm trying to think of the right way to talk about this. I'll say we plan for failure, right? Failures are going to happen. It's how we manage the risk around them and the tools that we give ourselves to deal with them that enable us to get through them. So, and I don't know the ins and outs of the software problem that Ingenuity had. Or if it was even a software problem. Sometimes we call them software problems because it's the only thing that we can change. But I don't know at the essence if it was a software problem. So anyway, we'll do, and I guess I'll talk a little bit the details. We have logs that print and get sent. We're collecting data while we're doing these different things. And so we have some insights that we get sent back to Earth into what's happening. We had to do some prediction of what systems we thought we might need to care about. And so we had to do some predictions to make sure that we record that information right ahead of time. And so when we have a problem like this, we'll do our best to understand the situation. Look at those log files, look at the data, just try to paint a full picture of what's going on. And then with that full picture, we try to understand potential causes. What might cause that flavor of problem, or what might cause this flavor of problem? And then we look at the data to see if any of those causes are corroborated. Try to see if any of those causes make sense. In some cases, we have to do testing on Earth to see if we can either replicate the problem, have the same problem on Earth as we did on Mars, or to see if we can develop a workaround for that problem. So the Mars yard and the rover that's in the Mars yard becomes infinitely useful in being able to figure out those kinds of things, especially when we get into more driving around and more sample collection activities. It's where we will, if we run into an issue, we will try to replicate it with the rover that we have here on Earth. And then if we can, then you can figure out a workaround and deploy the workaround. This is hard stuff, Scott. Like these are difficult challenges in a number of ways, doing things that we've never done before in so many different ways. never driven a rover like this before on Mars, never operated a sample caching system like this on Mars, never flown before on Mars, never made oxygen before on Mars. We have a variety of upgrades, and we have a great history, and we're using that history. Like the power system is the same as Mars Science Lab, the multi-mission radioisotope thermoelectric generator, the nuclear power battery that's by your right here. Is that your right here? Yeah. In the video.
Right over here. Ish.
Watch out.
So you just talked a little bit about how doing all these incredible things with robots and with autonomous or semi-autonomous vehicles. But earlier you also kind of mentioned, maybe we can talk a little bit more about that, the Moxie package that's on the rover as well. And I was wondering, because this is something I think a lot about as an IT guy, what's the right balance between humans and machines? And since we have such a great track record with robots on Mars, is there a place for humans in a Martian exploration, or do you think it should just be rovers, all the way?
So, in short, yes. I mean, yes, the humans should explore Mars. And I think about it in a couple different ways. I think about it, there's a technical aspect of that, like a human's ability to understand a situation, to process information, and to address something. We haven't gotten AI caught up to what humans can do, and maybe we never will. I don't know. I'm not going to talk about an iRobot or Terminator situation. So, but if you can imagine that pretty easily. We see this all the time on the International Space Station. When problems happen on the International Space Station in an area that we didn't expect a problem to have, we have humans there on the space station that can address it in person. On Mars right now, if we have a problem, like we're just talking, if we have a problem in an area that we didn't predict we would have a problem in, it gets really hard to fix. It gets really hard to address. And so from a technical standpoint, humans' ability to address problems and situations that we didn't expect in person far surpasses any robot we could possibly send. Not least of which, it's easier to design something for a human to use because we can use things in a bunch of different ways. When you're designing something for a robot to use, usually that robot can only use something in one or two ways. Like this big robotic arm, we have a drill on the end. It gets pretty hard to do much else than drill stuff. So if you have a problem and the answer isn't drilling, we're not going to solve it with our robotic arm. So that's the kind of like the technical flavor. But then there's this philosophical piece, Scott. Like, what is Earth? What is living on Earth? What is the universe? What do we get to answer any of those questions if we don't send a human there? Do we get to address the heart, and believe it or not, the heart of for a lot of people in the space program, for what the space program is to better understand what it is to be human. And how do I better understand what it is to be human if I'm only sending robots?
That's a great point. Well said. I don't think, as much as cool as it is to watch the video and receive all the data back, it's not the same as, not experientially the same as actually being there.
And I'm pro robot, by the way, right? Like I work at JPL. I am very pro robot. Like robotic missions need to be the precursors for everything. Robotic missions probably need to be done alongside human missions. There is no gap in need for robotic missions. I just think we get so much more as a human race if we're sending humans.
Yeah. So there may be among us today some future Martian astronauts who will be working alongside some robotic co-explorers. So that might be fantastic.
We're not far away from that.
Yeah, and well, first, I just want to give the opportunity if there's anything else you wanted to say about Perseverance before I ask my final question and then turn it over to our audience questions.
No, other than to say it takes a lot of people, a lot of smart people to come together to put together a mission like Perseverance. It's a giant team at not just at JPL and all of our partner organizations, and it's incredibly gratifying to work on such a large team, taking on such a hard task, and I'm going to jinx myself here, but so far things are going great.
Well, hopefully they will continue to do so. All the rovers have a good track record. So I will knock on the wood of my desk for
all the wood you can find.
So the final question is, because we do have a lot of kids joining us today, which is fantastic. If they wanted to do what you do, or if they want to just succeed generally in your field in space exploration and NASA, what advice would you give them? And
so the three things that I think about that that help me stay in the space program are: be flexible. There's a lot of ups and downs in the space program. Because NASA is a government organization, there's a lot of changes that happen that aren't driven by the technical needs of the science community. So be flexible with what you are open to doing and what you might look for, and the flavor of work that comes your way, if it's not exactly what you want to do. Be passionate to get through the hard times, keeping an eye on this big picture. And I always think about this stuff, like keeping an eye on what we're doing as a society and what we're doing as a space program. And by the way, like being on Mars with a Chinese mission, Tianwen-1, awesome. Being at Mars with a United Arab Emirates mission, Al-Amal, the Hope orbiter, awesome. But by the way, the United Arab Emirates used a Japanese launch vehicle to get to Mars. Like that, like if there's no other reason to have the space program, the international space program.
Yeah.
Right? And so being passionate helps get through the lulls in what we're doing in the space program, because there's always a high coming. And be open-minded. Be open-minded to working with others. Be open-minded to how you think about a problem. A lot of what we do is problem solving. So developing those problem solving skills and developing your approach to understanding situations and understanding problems, and being open-minded to how you might address a problem. A software problem might have a hardware solution.
Well said. So Jeff, thanks for taking the time to hang out with us. So those are my questions. I'm going to open it up to the questions to our audience. If you guys want to type your questions into the chat, and I will ask them. I do have two questions that were passed to us earlier, and they come from Nora Newton, who is I don't know. Sorry, Alyssa. I apologize. I think Nora's 4 or 5 years old. So she has two questions, which I think are fantastic. So one is she's 6. Nora, sorry, Nora. I apologize. Nora is 6. So the first question is, why is the rover white? So we Onondaga Free Library, we put together these Mars kits. Our children's librarian Maggie did a fantastic job, and one of them was to color in the rover to a landscape. And obviously in the coloring book, you get to make the rover whatever color you want, but the rovers typically tend to be white. Is that a conscious design choice, or is it just everything comes from wherever you get the raw aluminum and it's white? What's the reason?
So the aluminum's gray. There are some very technical reasons why. There's heat transfer reasons. There's I can see it on the surface of Mars reasons. There's also some non-technical reasons, like that's the color that paint comes in.
Right.
So I will say, Nora, white is not a design choice. There are lots of other colors that many of us would rather have. So color the rover whatever color you'd like. There might be technical reasons to make it blue.
Okay, and I think her second, and then the second question is also color related, and this one has to do though with the Martian rocks. Why is Mars red?
Iron. Mars is a little bit rusty. So it's oxidized iron that's kind of embedded across different areas of the soil. And because of that, you get little dust particles. So we call this, oh, she guessed it, good job, Nora. We have these piles of dust all over Mars. And you can see, if you've seen pictures, you can see the rover's already getting dusty. We call that regolith. So that regolith, because the Martian gravity is lower than on Earth, and Mars is pretty windy. There's not as much atmosphere, but the atmosphere that is there's a lot of wind. So that dust gets picked up into the atmosphere. So from Earth, Mars looks even redder than it is on Mars, because you have the surface of Mars is reddish. It's actually grayish, but it looks red because our eyes or whatever. But you also have the atmosphere filled with this dust, this Mars dust, that makes Mars look even redder than it is in person. Also, by the way, the daytime is red and sunsets are blue on Mars.
Oh, that would be, that goes actually to a question, which is from John Black. And his question is about, is it possible that humans could ever exist on Mars? And if so, what would it take, I guess? And one component that I was thinking about as you're talking about the blue sunset is, the psychology too of living on another planet.
Yeah, absolutely.
How different would it be, impact us psychologically to exist on a non-Earth planetary body?
Yeah, so there's the physical things that we need to stay alive, right? Food and water mostly, and air or oxygen in some amount. So we need those, so we need systems to promote that. If you've read The Martian or seen The Martian, they do an all right job addressing that kind of thing. Like, you might grow potatoes, you might grow something that can live in a not very friendly soil, because Mars doesn't have a super nutrient rich soil, because there isn't at least as many as yet living things in the soil. So you need all these systems to promote food, water, and air. So that's what MOXIE does. MOXIE is the precursors to a system to provide humans oxygen in some future exploration mission, some future human exploration mission. So if any of you kiddos do become Martian astronauts, thank MOXIE for being able to breathe on Mars. MOXIE, by the way, it takes a lot of power, so we can't do a whole lot else while MOXIE is producing its sevens of grams of oxygen. It's a lot of power. So you need food, water, power, and the systems to grow and make water and purify water. It's probably like the space station does a lot of water purification. And then you hit the nail on the head, Scott. Psychology. How do you not go crazy? Like, if you think if you saw, what is it, Castaway, with Tom Hanks, if you think he was talking to a volleyball that he named Wilson on an island that was still on Earth, imagine Matt Damon wouldn't be so cool on Mars by himself if his crewmates were just blasted away by some Martian storm. That won't happen, by the way. Martian storms don't happen like that. So psychology is such a big piece of it. Like, you need to you need to have you might send a psychologist, someone who really understands how humans work, in order to sort out problems. Astronauts are trained to live in tight quarters for long periods of time, but we've never lived on Mars. You've never lived so far away that you could be on a different side of the sun than Earth.
Yeah, that's crazy to think. I mean, it's a very nice day here in Syracuse, and so we were all outside like crazy people because we've been inside cold for months. And I, imagine what that would be like when there is no sunny day to wake up on Mars. You can go frolic outside.
Or arguably, they're all sunny days.
Oh, that's true.
But Mars being further away from the sun than Earth, you do get a lot less solar radiation. We think about it as radiation, solar radiation. So it's actually good for spacecraft because we don't have to worry about the effects, the bad effects of solar radiation. But it's bad for humans because we really like the vitamin D that the sun helps us produce here on Earth. So there'd probably be vitamin D supplements up the wazoo if you're a Martian astronaut.
Yeah. So the next question is also from Sophia, who asked a question earlier. And this one is actually going back to when you were on console for rocket launches. What was your favorite launch that you worked on or witnessed, or do you have a favorite launch? Or does seeing a million rocket launches get old at some point?
Not for me. I'll go watch a rocket launch any day of the week. I don't know. How do you choose a favorite? I really enjoyed, just personally working as a student on the Mars Exploration Rover launches. So the Spirit and Opportunity rover launches, especially as it's tied to what I've been doing on Mars 2020. Like, that's very personally gratifying. But in the 90s and early 2000s, there were a lot of shuttle launches, and to date, I've never seen a brighter launch in the middle of the night than a space shuttle launch. Like, it's like the sun's rising.
Cool. So our next question is from Marge Wellman, and so she wanted to clarify. So 10 years is the timeline for the samples to actually be returned to Earth, give or take?
Yeah, I mean, that's Jeff Megivern's analysis of what the project's doing. But I suppose you could say at best it's about 10 years out. Like super best, everything goes right, and we're fast at developing stuff. That would be the earliest. It probably is longer than that. So thanks for calling on my baloney. But 10 years would be like ripping fast. We get everything done and get things launched, because we still have to develop the systems, right? Then build the systems, and then we have to get there. And once we get there, we have to pick up the tubes, and then the timing has to be right to come back. So just like the timing has to be right to get there, the timing has to be right to come back. So, and I guess I could talk a little bit more about that too. After we crash land into Utah and go pick up these samples, the whole reason why we want to bring samples here is because we have way fancier equipment here on Earth that we wouldn't be able to send to Mars because it's too big and heavy to do like incredible science, incredible geology, and incredible biology, looking at samples here in person. So we'll send them. Actually, the plan right now is to send them to Johnson Space Center, to the labs that processed all of the lunar rocks, all the rocks from the moon from the Apollo program. We will send them through those same labs. They've been dusty for the past 50 years, so dusting things off. But
cool. They'll get some Mars dust that they can sprinkle around. So actually, you just brought up the moon rocks, and Ruth Thompson asked, is there any similarity between the moon and Mars? We're talking about going back to the moon with the Artemis project as a gateway to human exploration on Mars. Is there any similarities that are meaningful there?
So Neil deGrasse Tyson likes to talk about this concept that we're all made of space stuff, and the same speaks to all of the planets in our solar system. at some level, there's real chemical similarities and real base level similarities. At a macro level, not as much. Like there's no atmosphere on the moon. The gravity is a lot lower on the moon. The moon's way closer to Earth. So there are some things that are quite different. But what the moon enables and what going back to the moon really enables is establishing a station. You can establish a station on the moon or in orbit around the moon. And let's say you develop some launch capabilities, some rocket launch capabilities from the moon. So now you're launching from the moon instead of from Earth. You don't have to fight Earth's atmosphere. You don't have to fight the gravity of Earth because you're so far away already. The launch problem gets a lot easier if you're launching from the moon than if you're launching from Earth. So there's still a lot of science to learn about the moon. There's a lot of interesting chemicals like all the helium-3 and stuff like that. But I think for programmatically for the space program, it's about the launch capabilities that we can develop around the moon in order to get to places like Mars.
Cool. So I think we have time for one or two more questions. So the next question is from Courtney Black, who's one of the board members of the Strathmore Speakers. And so she asked, did Mars lose its atmosphere? And if so, could Earth one day look like Mars if we experience a large-scale climate shift?
So Mars hasn't lost all of its atmosphere. It has about 1% of the atmosphere of Earth. So while we have 760 torr. Torr is a unit of pressure. So on Earth at sea level, it's 760 torr. On Mars at ground level, it's 7 torr. So you can think that's the weight of the atmosphere sitting on your shoulders. And so it's about 1% of the atmosphere of Earth. And to address your other question, it's not hard for me to imagine because of climate change and because of other naturally occurring solar system and space changes that someday Earth could look a lot like Mars. Solar systems tend to go in that direction than the other direction. It's kind of related to how everything heads towards chaos. And what I mean by that is, if you think about entropy and the idea that molecules are moving and moving and moving, and eventually they turn into heat because they're moving so fast. And if they're hot enough, they can drift off and leave Earth altogether. Like hydrogen can get hot and leave Earth altogether. If that happens enough, then you lose your atmosphere. So if things get hot enough for long enough, you end up with not any molecules around Earth. In that, so yeah, Courtney, it's not too hard to imagine that scenario.
That would be terrible. Everyone out there, hold on to your molecules. And then that a question then that is the inverse of that. Could we transform Mars into Earth? If it's possible for the process to go in the chaos direction, can we impose some order on the system and turn Mars into a second Earth?
So to go from order to chaos, it doesn't take a lot of energy. To go from chaos to order, it takes a ton of energy. So theoretically, I suppose you could imagine you have some atmosphere making system on Mars, or there's this concept of terraforming. You terraform Mars, and you could take up a bunch of manure, right? Take up a bunch of nutrient-rich soil, and you could probably process the Mars soil and force it to grow stuff. It's really cold though, so like the day there, daytime, around about -40, -50 Celsius. So it's chilly. Yeah, it's chilly. So you'd have to find a pretty resistant plant grow there. And I don't see a lot of plants in Antarctica, so I don't know. Maybe you could. Do I think it's practical? No, I don't think it's practical. Theoretically, you could probably do it, but I don't think it's reasonable to do.
Okay, so that makes minus, what was it? Would you say minus 59 in the daytime? That makes a Syracuse winter look tropical.
That's right. Yeah. You'd come back from your trip to Mars after a big whiteout, a big blizzard, and you'd take off your coat.
Yeah, seriously. So, okay, so our final question here, I guess, unless anybody else has anything they want to add into the chat, is from Dara Megivern, who notes, I'm gonna quote her, your favorite cousin. I don't want to start family troubles there, but she's claiming to be your favorite cousin. And she asks, how is the rover supplied with power? Is there a battery? Like, does it have a little lightning connector and it just plugs into a 110 volts there on the Martian surface? How does it get power?
Yeah, we have USB-C on the rover.
Nice. That's great.
Well, hello, Dara. And as long as none of your brothers and sisters are on the call, I will agree that you're my favorite cousin. But if Connor's on, I don't know, Connor's pretty cool. So power for the rover, we essentially do have a big battery. So we were joking, the thing by your head, Scott, is the nuclear other side.
Yeah, there we go.
That guy right there.
Right here.
That is a giant nuclear powered battery. And so for us, for this project and this rover, that's where all of our power comes from. And so then we have a power system that takes the power that battery is generating and flows it through the rest of the rover. That's not always the case, and it's probably easy to say it's not even usually the case. Usually we use solar power. And so a lot of our landers, including the InSight lander, Mars InSight, that landed a couple years ago and is doing great science, digging into the soil and measuring Mars quakes, is all solar powered.
Cool. That must be problematic with the dust, I would imagine. Collecting on there.
It's a race between the mechanisms breaking down and the solar panels getting covered with dust.
And so with that nuclear powered battery, what's Perseverance's lifespan? Will we get samples back and Perseverance will still be out there, maybe not returning samples, but looking at something interesting? Or by the time we get the samples
something else will break down on the rover before that battery ever goes dead. That part of the Martian is probably not too off. Like, he'd be getting a lot of radiation poisoning, Matt Damon would. But that he'd be able to dig up that battery, and that battery would probably still be usable.
Oh, that's pretty good.
We put a lot of margin into our power requirements, and so there's a lot of space between what the battery can do and what we actually need for the rover.
Cool.
I will mention an upcoming project called Europa Clipper. So there's this dual mission. One's funded and underway, and one isn't fully funded yet, but would be a follow-on. So there's Europa Clipper and the Europa lander. Europa Clipper is an orbiter that we're going to send to Europa, which is an icy moon of Jupiter. So we'll have this orbiter circling Europa, picking up data to understand what's around Europa, what the surface looks like, picking out landing locations. And then we have a follow-up project that, like I mentioned, needs to be funded, but we're doing some R&D for it now, called Europa Lander. That's going to land on Europa and start digging into the surface and digging into the ice and trying to understand what lies beneath.
Awesome. That sounds fantastic. And I hope some people who are on this call will be working on that project, and we'll have them on the Strathmore speakers to tell us all about that.
Absolutely.
So Jeff, thank you very much for taking the time to talk with us today from California. And it's been fantastic.
Yeah, great chatting with you, Scott. Thanks, everybody.
So I'm going to turn it over to Mary Beth, who's going to take us on back to our lovely afternoon and tell us about some upcoming Strathmore the final Strathmore speaker series for this season.
Thank you, Jeff, for joining us here today to share your fascinating story. On Thursday, June 10th, we'll be back to our 7 p.m. slot with Joey Patterson, an Antarctic marine technician and tall ship sailor. Her talk is titled Icebreakers, Zodiacs, and Elephant Seals, Antarctic Science and Life as a Marine Technician. She'll share her stories about life on an icebreaker, close encounters with wildlife, and scientific expeditions she has facilitated. You can find updates on the series at our website, strathmorespeakers.com. Thank you all for joining us today, and we hope to see you again in June. Bye-bye.
Thanks, everybody. Thanks for joining us. Go enjoy the warm weather.